concepts. So the screen is visible, right?
Yes, ma'am.
Okay, so first of all, we'll discuss a little bit about the concept of stability. The stability concept obviously will come later on in the later modules when we will be discussing in much more details about how a control system stability works and what all factors are affecting the stability. But just to give you a brief idea about what stability of a system means. So if you remember, we had talked about different types of signals that can be present. So the type of signals where like the signals can be linear signals, non-linear signals or systems, then time variant, time invariant. So different. So we did a classification of different kinds of systems. So another type of classification of these systems is known as bounded signal or unbounded signal. Okay, so what do you mean by a bounded signal? So by definition, it goes like a signal is said to be bounded if it is having a finite value at any instant of time. So if you take this, for example, if you see this, take this figure. So here you see that for okay, so here you see that this graph is basically, or this signal is basically decreasing with time. So that means it started off at time t equals to something. It started off at some finite value and it is slowly gradually decreasing it with time. So that means that this will be known as a bounded signal. Similarly, for this one, you see that you will get at whatever time instant you will get a finite. At least if you follow this trend, if something else doesn't happen unnaturally, if this trend is followed, so that means that the signal will have a finite value for at any time instant. And if you get a signal which is like which is not bounded, so unbounded signal means that it might have an infinite value at any instant of time. So for this signal, you see that if you follow the trend, so that means this is sort of exponentially growing a signal. So that means it might so happen that at some later point or at that time t equals to infinity, the value of this signal will reach infinity. So that means this is known as an unbounded signal. Similarly, here you see that the oscillations, they are keeping on, they are gradually increasing with time. So that means at infinite time, you will get an infinite value of the signal. So those kind of signals which will have an infinite time, not an infinite value, not necessarily at t equals to infinity, it can be at any point. If at any point of instant or at any instant of time, if the value of a signal is not finite, then we say that it is an unbounded signal. And if you want to represent, so mathematically, if you want to represent, so a signal is bounded if there is a finite value, if there exists a finite value b such that the value of b is greater than 0 and the signal magnitude, it never exceeds the value of b. Okay, so if you are dealing with a continuous time signal, so then the magnitude of that continuous time signal, let's say yt, should always be equals to less than equal to t for any real value of t. Similarly, if you are dealing with a discrete time signals, in that case, the magnitude of yn will be equal to will always be equal to less than equals to b for any value of for any integral value of n. So if these conditions are satisfied, then you say that the signal is bounded. Similarly, so this concept of stability, it comes from this bounded input, bounded output kind of a scenario. So bounded input, bounded output kind of scenario means if you are provided with a system and the system you are giving a bounded input to that system. So in that condition, if the output that is being generated by the system, if that output is bounded, then it is said that the system is stable. So you will say that a system is stable if for every bounded input that is being applied to the system, the output that is generated is also a bounded signal. But however, if the system will be unstable if you are providing any bounded input, but the output that you are getting for that corresponding bounded input, if that output is unbounded, then we say that the system is unstable. So if you see this figure, so let's say that you have a bounded input, something like this, and you're applying it to a system. And if your output is also a bounded signal, so that means your system is stable. But in the second case, you see that you're applying the same bounded input but you're applying it to a different system, and because of that the output that you're getting is that it is actually increasing and going on to infinity. So that means the output that you are getting, that is an unbounded signal. So in this kind of a scenario, you say that it is known as an unstable system. So that's why you said that bounded, so BIBO system, so bounded input, bounded output system is stable. The other way of representing this is that the bounded input, bounded output system is stable if and only if the impulse response of that system is absolutely integrable. If you see the mathematics, so let's say that you have an open loop system. Okay, so you just have a system here which is represented by G, your output is C and your input is S. So that means CS will be equals to GS into RS. Now, if you are providing an input of RT and correspondingly you are getting a CT and your G of T is the impulse response of the system, then if you find out the time domain value of this output, so that time domain value will be given by this kind of an expression. So using that convolution property of the Laplace transform, you can find the output value in that the output signal in time domain. So if you take the magnitude of both the sides, so this will be equals to magnitude of CT, and so the magnitude of will give you an expression like this. Now if the absolute value of this integral is not, so you can say that, so this is the absolute value of the overall integral. Okay, so then if you take the absolute value of each of this terms, so that means the absolute value of an integral is not greater than the integral of the absolute value of the integrand. So this is a property of convolution, and this is a property of while dealing with magnitudes and all. So you will have that the magnitude of CT will be always less than equal to integration of magnitude of these two terms which we are actually integrating. So, and now if you consider that if R, the value of, so this is your input R of t minus tau. So if R of t minus tau is a bounded input, so that means bounded input means the value will be some less than equal to some m or b, which is a value less than infinity. If that is the case, then the output, this CT should satisfy less than equals to m integral of this thing. So the output, so this is the final output of the system. So if you see that now, if this output CT, it follows the criteria that the output is bounded when this value is less. So this integral is less than infinity. So if this integral is less than infinity, then you can say that the magnitude of CT, so the overall magnitude of the output will be less than infinity and it will be a bounded signal. So then if this condition is satisfied, so that means the impulse response of the system is absolutely integrable. In that case, the system is known to be a stable BIBO input, BIBO stable system, bounded input, bounded output stable system. For understanding the physical interpretation, so physical interpretation, as because we are talking about the integral, so that means the area under the absolute curve of the impulse response should have a finite value when it is evaluated between t equals to 0 to t equals to infinity. Okay, so if these conditions are satisfied, you say that the system is stable considering BIBO stability. Okay, clear?
Yes, ma'am.
So the next topic that we will just brush up upon is that of the rotational systems. So we had already discussed earlier about translational mechanical systems, wherein we saw that a mechanical system consists of what? There can be a combination of mass. There can be mass, spring, and some kind of friction or a damping element. So that was a translational system. So if you are, so the corresponding rotational system also can be drawn. So in case of a rotational system, it has the mass is replaced by, so it consists of a rotatable disk and it has a moment of inertia of J. Then there is a shaft. The shaft has a stiffness constant of K. And then this disk rotates in a viscous medium, and because of that rotation, there will be some viscous coefficient friction generated, and that viscous coefficient is given by F. So now if you apply a torque T, previously we were applying a linear force F. to the spring mass damper system. So in case of a rotational system, we will be applying some torque T, and so this torque, after application of this torque, what will happen is that it will tend to rotate the disc. So now if you draw the free body diagram of this system, so you see that the force applied or the torque applied is in this direction, and all the other forces, they are so these are like so the effect of friction and the effect of shaft stiffness. So these are all they all occur in the positive. They try to restrict, or they try to oppose the direction of motion. So that means, so the overall so T is, if you write the differential equation of this free body diagram, then it will be the torque applied T minus the effect of this due to the viscous coefficient, viscous friction. So that will be equals to F of theta dot. Then another negative force which will be applied, that is because of the shaft stiffness, that is K theta. Overall, that this is the overall force which is being, or the overall torque which is being applied to this disc, and because of that it is getting some motion, or it is rotating by an angle of theta. So that will be equals to J theta double dot. Okay, so this is how you can take the you can analyze a rotational system. Now, in case of a rotational system, there is one more thing that is known as gear or gear train. So this gear basically is a device which is used to transmit torque. Okay, so gear trains are mostly, they are used to so if you have like you are connecting one motor to a load. You have a rotating motor and you are connecting it to a load. Okay, so in order to match the two torques of the motor and the load, you need a system which is known as a gear train. So the gear train, basically the mechanism, it acts more like a transformer, you can say. So it is more like, it is equivalent to the transformer in an electrical system. So let's say if you have a servo motor, so servo motors, they generally operate at high speed but low torque. And now let us say that you are connecting this servo motor to drive a load, but the load has very high torque and low speed. Okay, so now, so you can see that there is a mismatch between the torque values of the motor and the load. So in order to match the two torques, the value of the torques, what we use is that we use a gear train kind of a mechanism. So in this gear train, so basically so you have like two gears. So let's say you have something like this. So this is gear number, this has N1 teeth on it, this has N2 teeth, and if it is connected, so here there is a, let's say you have the motor on this side and you have the load on this side. Okay, so this is how the gear train is actually connected, and in order to match the loads of, in order to match the torque of both the motor as well as the load. Okay, so if the number of teeth on the surface of the gear, that is, and let's say for this is N1 and this is N2, so that the number of teeth on the surface of the gear, that is proportional to the radius of the gear. So you can write that R1 N2 will be equals to R2 into N1, and the gears are, they are like this kind of a structure. So you have a small gear like this and you have a big gear, and these two, they are teeth, so they rotate on each other. Okay, so since if you are if we assume that there is no slip between the movement of the gear, and that while it is moving, every teeth is getting matched with the other teeth of the gear, in that case the distance traveled along the surface of each gear, that is also same. So that means you can write that if the angular displacement is θ1 and θ2 for the two gears, so the value of R1 θ1 will be equals to R2 θ2. And if you assume that there is no loss in the system, then the total work done by one gear should be equal to the total work done by the other gear. That can be represented as T1 θ1 equals to T2 θ2. So from these three equations, you can write that if you take a ratio of torque 1 in this gear to torque 2 in the other gear, so that will be equals to θ2 by θ1, or if you want to represent it in terms of velocity or acceleration, so that will be equals to θ2 dot by θ1 dot. So now if you are, so let's say that you have, so this is a gear train kind of a mechanism. So you have a motor on the primary side and you have a load on the secondary side. Okay, so here we are assuming that the shaft has infinite compliance and the shaft stiffness is 0. So that means this turn, this K turn, we are assuming that this K turn, K theta turn is 0 for this kind of an operation. Okay, so if you consider that, so now what we'll do is that for the shaft 1, so you will write the differential equation of while modeling the shaft 1. So that differential equation will be given by, if Tm is the torque which is developed by the motor, so then it will be J1 theta 1 double dot plus F1 theta 1 dot plus T1, where T1 is the load torque which is applied or on gear 1 because of the rest of the gear train. Okay, because of this, whatever effect of this second gear train is there on the first gear, that is known as T1. Similarly, if you write the equation for the second shaft, so that will be given by this equation. So now if you write, if you combine these two equations and you remove the value of T1 and T2, so you will get an equation like this. So by solving that previous two equations, just eliminate T1 and T2, you will land up with an equation like this. So from there you can see that if you want to remove, again if you remove theta 2 from this equation and you represent everything in terms of theta 1, then you will find that the equivalent moment of inertia of this whole gear train when you are referring to shaft 1. So from this shaft 1 point of view, that will be given by this equation. Similarly, you can find the equivalent viscous friction and all this from shaft 1 point of view. From shaft 2 point of view, if you want to do the same calculation, so what you have to do is that you have to remove the value of theta 1, you have to substitute theta 1 and you have to find the expression in terms of the load current and the load torque as well as theta 2. So from there you can find what will be the moment of inertia, viscous friction and load torque, everything with respect to when you are looking from shaft 2. So this is how a rotational system is usually connected using a gear train kind of mechanism. So if you see the this actually we had already talked earlier for force voltage analogy. So you see that the torque is equivalent to force, or in case of force voltage analogy, torque will be equivalent to voltage source, inertia will be equivalent to inductance, and so on and so forth. Similarly, once you have found this equation, you can, for the force current analogy also, you can find which all terms or elements in the mechanical rotational system will be equivalent to what electrical parameters. So then the last topic before we move on to practicing some problems is that while analysis of this mechanical systems, so there are two ways of so first of all, when we have an electrical system, it becomes easy to analyze because we know that we can apply KCL, KVL. So you have been given with an electrical system, you can find out the nodes and loops and you can apply KCL and KVL and find out what is the final differential equation model of the system. But in case of a mechanical system, so there are two ways of doing this analysis. So the first one is that you draw the free body diagram of corresponding to each mass or inertia element that you have in the mechanical system. In the free body diagram, what you will have is that you will for corresponding to each mass, you will see what all are the forces that are being acted upon that mass and what is the direction of that force. So once you have come up with the direction of the forces and the magnitude of the forces which are being applicable on each mass or mass in case of a rotation, in case of a translational system, and inertia in case of a rotational system, then you apply the second law of motion and you find out what is the differential equation which is governing the whole system. And then the second way of doing is that that is known as a nodal analysis. So in case of nodal analysis, what you do is that you first of all you identify the number of, so you are given with a mechanical system and you first of all you identify the number of nodes in the system. So what are the nodes? So if the mechanical system, the number of displacements that are present in the mechanical system, that will be equal to the number of nodes. And so those will be known as the displacement nodes. Okay. And then you have to take another, so there will be some fixed portion in the, so if you see this, in this figure, you see that this is your reference. So in this figure, you have only one displacement, you have one mass and the only one displacement xt. So that means xt, corresponding to xt, you will get a node, and there will be another node which is the reference node corresponding to this reference point. Okay, so first of all, the first step is to identify what are the nodes present in the mechanical system. Okay, so once you have identified that, then what you will do is that first you will connect all the mass or inertia elements that are present between the relevant displacement node and the reference node, irrespective of its position. So irrespective of whether it is connected between the reference node and the displacement node, or whether it is connected between this displacement node and there might be another displacement node connected in cascade to this. So irrespective of where the mass is, the position of the mass, you will connect the mass between the corresponding displacement node and the this reference node. So that will be the second step. In the third step, you will connect all the spring and the damper elements which are present between the relevant nodes, relevant displacement node or the reference node, depending on where they are connected. So in this case, so this spring will be connected between node X and the this reference node. This damper will be connected at node X and at the between the displacement and the reference node. But in case of, you see, this mass is basically connected between so this is mass is not directly connected to the reference point, but still for connecting the mass we will not we will not take into consideration what position it is there. Okay, so once you have connected all the circuits, all the elements in that way, then what you do is that and then you obviously you need to connect the force or the torque which is the input to the system between the relevant nodes. So once your nodal analysis, so that figure is drawn, then what you do is that for each displacement node you apply the Newton's law of motion and you find out and you analyze the system. Okay, so we'll see one example and then it will be more clear. So once you have done the nodal analysis, so then you can simply draw the force current analogy or the analogous electrical system or the analogous for the force voltage analogy also. So in case of a force current analogy, what you will do is that you will just replace, you'll have that whatever nodal equation, like this diagram you have, simply replace the mechanical elements with the analogous electrical elements. So analogous electrical elements means from this figure, from this table, you can see that corresponding to which element, what is your corresponding value of the electrical quantity. So you just replace those and the nodes will be same, and each node will be will represent in the electrical system, each displacement node of the mechanical system will be equivalent to a voltage in the electrical system. But in case of force voltage analogy, what you need to do is that instead of just simply connecting all the, so you have here, you are mostly, since you are doing a nodal analysis, means you will have a parallel combination of different circuits. But when you are using a force voltage analogy, you have to, all the parallel elements, they needs to be replaced by their corresponding, obviously, electrical analogous element. But all the electrical analogous elements, they should be given, provided in a series form. So it will be in a loop form instead of being connected in parallel and in force current analogy. For force voltage analogy, the mechanical elements and their corresponding when you are drawing the electrical circuit, it will be connected in series, and each displacement node in the mechanical system, that will correspond to each current in the loop of the electrical system. Okay, so what we can do is that we can just take one example for this analysis of mechanical system, and then I think it would be much more clear to all of you. Okay, so let's say that you have just 1 minute. Okay, so let's say that you have a mechanical system, a rotational mechanical system. Okay, so you have J1 over here, something like this. Okay. So this is your reference point. So this is J1, and there is so there is this friction, viscous friction here also. This is J2, this is J3. So the frictional constants are given here. This is moving by an angle of θ1, θ2, θ3, and this is, let's say, K1. So these are springs, K2, K3, and the applied torque is T. Okay, so now can you draw the free body diagram of this system, or the nodal analysis for this system? How would you first, let's say you want to do that nodal analysis, how would you first proceed? So how many inertia elements are there? Three inertia elements. Okay, so and how many, so for nodal analysis, what you need to do is that first you need to identify how many displacements are there. So how many displacements?
Three displacements and one
Three
angle.
displacement. Yeah, so let's say this is θ1, θ2, and you have another displacement θ3 over here. Okay, so and you have another reference displacement. So let's say that reference node is here. Okay, so let me draw it like this. Fine. So now what you will do is that first of all you will connect the inertia elements corresponding to the irrespective of whether it is the position of the J1, you will connect the inertia element between the corresponding displacement node and the reference node. So what is the inertia element present between θ1?
B1, the first one.
First one. B1 is not, the inertia is given by J1. B1 is the viscous coefficient, viscous friction coefficient. So that means you will have, let's say you have, so you represent it by this. So you have J1 over here. Similarly, what will be the cases in for J2 and J3? Where will they be connected?
θ2.
So this will be J2, right?
Yes, ma'am.
Okay, so now, so the inertia element is done. So now what you are left with is that you have this friction coefficient and you have the spring coefficient. So now what you will have to do is that you will have to connect the corresponding. So now let us connect the friction coefficient. So for this B1, where will it be connected? Between what nodes B1 will be connected?
The θ1 and θ2.
B1 between θ1 and θ2?
Yes, ma'am. No,
B1.
No, ma'am. It should be between J1 and θ1.
Between J1, so it won't be between J1. So the J1 is basically the property of this inertia element, and B1 is the friction which is happening at this surface, right? This overall element that has, so B1 is another property of that. So that means it will be between this node θ1 and what is this bottom node? What is this node?
Ma'am, the ground one, the bottom one.
The reference node, right? So you will connect, let's say you connect it some. So this is your B1, right? Similarly, tell me the positions for B2 and B3.
Yes, ma'am. It will be between theta2 and reference and theta3 and reference.
Yes, so you will have B2 over here and you will have B3 over here. Now what we are left with is that you have to connect this K1, K2 and K3. So what will be the positions of K1, K2 and K3?
Ma'am, between theta1 and theta2, we will have K1, ma'am. Between theta2 and theta3, K2, and between theta3 and ground, reference, we will have K3.
Yes, between this thing and ground, you will have K3. And then the last one is this torque. Where will the torque be connected?
Ma'am, theta1 and reference.
Yes. So you will represent that, let's say this is as a torque T. So this is you can say that this is the nodal analysis of the system. Okay, so this is the nodal diagram for this mechanical system. So now for doing the analysis, what you will do, so you have like 3 nodes. So you have one node here, and the third node here. So in each node you can apply the so this T, let us say that this one is going is in that upward direction. Okay, so you can take it in the downward direction also, but just take one reference direction for this input torque. Okay, so if that is the case, then you can apply the you can write the nodal equations corresponding to these terms at the 3 nodes. So let's say first of all at node theta1. So what will be the equation? So there are like 4 elements which are connected to node theta1, right? So you have to write the corresponding expressions for contributions for each of these elements, and then simply by the nodal analysis, like everything coming together. So whatever like in case of KCL, we had seen that all the input currents which are flowing into a node will be equal to the summation of all the currents which is flowing outside the node. So in a similar way, so if all the signals which is going into the node will be equal to summation of all the signals which is going out of the node. So if you apply that principle, what will be the equation at node 1 or node theta1? So what is the contribution for J1? What will the corresponding like torque contribution for J1? So this was the basic equation governing the torque for moment of inertia. If you take moment of inertia into consideration, right? J into theta double dot, where theta is the angular displacement, obviously. Correct?
Yes, ma'am. J1 into theta1 double dot it will be.
Yes. So, and what will be the direction of that torque? Will it be in the same direction as the applied torque, or will it be in the opposite direction?
Ma'am, it will be in the same direction.
Why?
Ma'am, in the diagram you can see that the direction of torque and theta1 is in the same direction.
No, theta1 is the overall, like after applying this torque, this whole system is moving in this direction. This is the direction of displacement or direction of motion of this whole system. But when you have a system, so if you are applying some some external force to it, what is the inherent property of that system? What will that system want? Will it want to change its position, or will it comply with the input force which is being applied, or it will try to resist that force? What is the inherent nature?
Yes, ma'am.
It will try to
resist.
It will try to resist. So that means it will be the torque which the moment of inertia is providing, it will be in the opposite direction of the input torque.
Yes, ma'am.
Right. So that means, so if you write, so let's say if you're writing this torque T, so this will be, or rather minus J1 theta 1 double dot. Okay, fine. So what about the other contributions?
Minus J2 theta 2 double dot and minus J3 theta 3 double dot.
No. First, so we are considering only doing the nodal analysis as theta 1. J2 is not connected with theta 1, right? Theta 1 you have only T, J1, B1 and K1. Only
Yes.
These four parameters are connected to theta 1. So we are only looking into this part of the circuit. So you have to find what is the contribution for this B1 as well as this K1.
Ma'am, B will be like K1 into theta 1.
Not K1. So for this damper, for this viscous force, it will be B1 into theta 1 dot. So if you see this, yeah. So here you see that when you have a viscous force, so the contribution for the viscous friction, that is given by F into theta dot. F or whatever constant is there, F into theta dot. And the contribution for this shaft or this spring, that is given by K into theta. And this J into d theta dot theta double dot, that is the max, like after what is the overall contribution. Like obviously if the, since this is this disc is moving after applying some torque T, this disc is moving by an angle theta. So that means, so if you see that, so this will be the acceleration, d2 theta dt2 will be the acceleration, and the overall torque will be force into, you can say that J into d2 theta dt2. So similarly here you will find that, so you will have, so the contribution, the input was this, and you have two opposing forces, one due to B1, another due to K1. So that opposing force will come as minus B1 into theta 1 dot, and minus for this K1, what will be the opposing force? K1 into?
K1 into theta 1.
Will it be theta 1, or because K is connected between theta 1 and theta 2?
The difference of thetas.
So it will be theta 1 minus theta 2. So you have to see, because see when you are doing, and so this is a similar kind of an analysis if all these elements were replaced by like resistances, let's say. So for this, for if you are doing the nodal analysis, or if you are applying KCL, so for this K1, it will be obviously the current flowing will be theta 1 minus theta 2 by K1. I mean, if it were an electrical system, it will be theta 1 minus theta 2 by R1. Similarly, in this case also, you will have to consider the values and between what nodes. Since see, this J1 and B1, they are connected with the reference node. So that means, so that reference node is 0. So it will be theta 1 minus 0. So which is equivalent to theta 1. But K1 is not connected between theta 1 and 0. Or the reference. So it is connected between theta 1 and theta 2. So that's why you have to take theta K1, theta 1 minus theta 2. So this overall, so this is going in and all these are going out. So this overall will be equals to 0. Similarly, the equation you can write for theta 2. Can you quickly tell me what will be the nodal equation at theta 2? So theta 2, you have B2 connected, J2, K2 is connected, K1 is connected. These four elements are connected at node theta. So you have to find what is the contribution for each of these elements.
Ma'am, it will be like J2
K2
theta double prime.
Sorry, can you repeat again?
J2 theta 2 double prime.
J2 theta 2 double dot,
plus B2 theta 2 dot.
Okay.
Plus K2 into theta 2 minus theta 3.
K2 into theta 2 minus theta 3 will be equal to
0.
Why will it be equal to 0? So what about the contribution of K1? So you had four elements, right? K2, B2. So you have J2, B2,
yes,
K2.
It would be K1 into theta 1 minus theta 2.
Will be equals to K1 into theta 1 minus theta 2. Yes, so this is the equation for node 2. So similarly, you can write the equation at node 3 also. So if you write the equation at node 3, so let me just quickly write it. So here you have 1 K3, B3, J3 and K2. So for this K3, and here you see that all these three are connected between theta 3 and reference, and only K2 is connected between theta 2 and theta 3. So you can write this at this node. This is the equation. So now if you want to, so this is like the mathematical relation between, or the differential equation model of this mechanical system. So now if you want to draw the corresponding force current or force voltage analogy. So if you want to write the force voltage analogy, so first of all you see that there are three displacement nodes. So that means there will be three loops in the force current force voltage analogy. Okay. And if you remember for the torque, so torque will be represented by a voltage source. So you will have a voltage source, let's say some ET over here. Then your if you go back to this figure, you see that inertia is equivalent to a resistance, viscous friction is equivalent to, inertia is equivalent to an inductance, viscous friction to resistance, and spring stiffness is equivalent to 1 by C. So you can simply represent like J1. So you will have in the first loop, so you will have 1, 2, 3 and 4 elements in the first loop. So just represent them like, so you have an R over here, then you have L over here, and you have a corresponding capacitance. And for this capacitance, you see that this capacitance, this is between the two nodes. So that means it will be a common element between two loops. Okay, so if it is a common element, so that means it will be represented somewhere over here. Similarly, if you want to draw the rest of the circuit, then you will similarly for this second loop, you will find that again you will draw this, you will have another resistance, and then you will have a C over here. And so this is your first loop, which is I1 corresponding to theta 1 in the mechanical system. In the second loop, it will be I2 corresponding to theta 2 of your mechanical system. And the third loop will look something like this. So this will be, let's say, R1, L1, 1 by C1, R2, L2, 1 by C2, R3, L3, 1 by C3. Okay, so this is how you will correspondingly, so from this nodal equation of the mechanical system, you will convert it into a force voltage analogy. In case of a force current analogy, the only thing that you need to do is that for force current analogy, So the torque will be represented by some current source. And here you will just replace all these elements with the corresponding, so in this same configuration, so you will have something like this over here, some resistance, inductance, and this K1 is, in case of forced current analogy, K1 will be equal to the inverse of inductor. So you will not have any capacitance over here. Inductor will be connected to the next one. Okay, so this will be the electrical circuit when you are dealing. So this will be some voltage V1. This will be another voltage V2. This is another node voltage V3. Okay, so this is how you convert a mechanical system into an corresponding or equivalent or analogous electrical system. So is it clear? Did it make sense?
10
minutes.
Yes.
10 minutes और.
Okay, so now what we can do is that let us try to solve one question for that sensitivity analysis for you to.
One doubt in the previous slide.
Yes.
Actually, the R1 and L1 according to that was related to ground, no ma'am, like reference point. And the capacitor was the connection between θ1 and θ2. So capacitor should be connected like in series with θ1 and θ2. And the RN that should be connected to the ground.
You are talking about the force voltage or force current analogy?
Force voltage.
So in case of a force voltage analogy, so we are converting this whole. So here you see that it is connected in a branch form, right? So everything is connected between θ1 or a one node, one displacement node and another reference node. When you are drawing the force voltage analogy, each node will be converted into a loop. In the electrical system, if you are using force voltage analogy, so this whole thing will be converted to one loop. So if you have one loop, so this whole part is now converted to one loop, which is given by this. So this R1 and L1, these two are corresponding to J1 and B1, which were connected between θ1 and the reference. So you have it in series. So these three elements will be in series, and this one that will also be in a series, but this will be shared by the next part of the circuit as well. So it will come as something common as here. Got my point?
Yes, ma'am.
But when you're drawing the force current analogy, in that case, you will keep the same branching configuration. So here you see that, so this branch is not there. So here you are just replacing this R. So in case of a force current analogy, torque will be equal to current, inertia will be equal to capacitance. This will be equals to 1 by R, this will be, and torque, the stiffness of spring will be 1 by L. So here you will have, so this for the corresponding J, you will have 1 by R. Here you will have 1 by L, and this one you will be, that will be C. This is R1, C1, L1, and this L1 is here. You see that this K1, which is corresponding to 1 by L1, that is connected between two displacement nodes. So here also it will be connected between two voltage nodes in the electrical system. Okay. So the main difference between force current and force voltage analogy is that in case of a force current analogy, you can simply replace, so whatever is the nodal analysis or the nodal diagram that you have drawn, you just simply replace the corresponding elements, mechanical elements with the analogous current electrical elements. But if you are using force voltage analogy, then each branch or each node will be converted into a loop. So that means a loop means whatever was there in parallel in the mechanical system will be reflected as in a series combination in the force voltage analogy. That's why we are having this. Okay.
Yes, ma'am.
Okay. So now if you let's say do quickly do a sensitivity analysis. So let's say you have been given with a so I had already shared a scanned copy of the problems which are there in the book of Nagaraj Gopal. So you can go through that. And
in that PDF, are there questions regarding mechanical systems, also thermal system, this type, just like you made us solve the last one?
So those things, I think in that the PDF version of the book which is already available in the internet, I think those pages are already there. That's why I did not scan them.
No, so, I didn't know that.
Okay, yeah, because I checked and then I saw that those pages are already there. That's why I did not scan them. And but for the sensitivity analysis, these like maybe 1 or 2 pages were there, but not all were there. So that's why I scanned these pages and uploaded for your reference.
Okay, ma'am. I'll refer the book.
Okay. So you all have the PDF copy of the book, right? Otherwise, I can upload that PDF as well. So let us say you have been given with a system like this. Okay, so this is a block diagram of a system, and this is your output theta 0. Theta r is your reference. ES is the difference between the output and the input, and DS is basically a disturbance, or you can say this is a load torque. Okay, so now what you have to find out? You have to find out what is the value of TDS. So TDS is given by, so theta 0 S by by ds, considering theta rs is equals to 0. So what will be the, so first of all you have to find what is the value of TDS, and then you have to find what is the sensitivity of TD with respect to, let's say, Ka. Let us say you want to find it only with respect to Ka. So can you find out what will be the value of TD of S?
Yes, ma'am.
So in the first case, when we are considering that theta r is equals to 0, what will be your forward path gain or forward path transfer function?
Ma'am, 1 by s into js plus 1, ma'am.
That is the forward path transfer function. And what about the rest of the, and what will be there in the feedback path?
Ma'am, feedback pack will have 1, ma'am, because we have nothing here.
Why nothing? Because here you see that theta r is equals to 0. So that means this input now is equals to 0. This is 0 means this comparator basically it has only theta 0 is directly coming. So ES will be, previously ES was equal to theta r minus theta 0.
Yes.
Now if you consider theta r equals to 0, so that means ES will be nothing but minus theta 0. So this will be, so now ds is the input, since we are finding TDS equals to theta 0 by ds. So output is theta 0 and input is ds. So whatever else, and this is the forward path. So the rest is actually, so if you draw like if you redraw this circuit, so now you will have, so ds is your input over here. So this forward path is gs, that 1 by that thing. Your output is theta 0 s, and between theta 0 s, so this is getting connected. So you have ka over here, then you have kt by rf over here, and this is coming here in the positive direction, correct? So theta 1, theta 0 is now coming through via Ka and Kt by Rf, and it is going into this error comparator. So this would be your overall transfer or the block diagram if you consider only ds as your input and you remove the value of theta r. Am I right?
Yes.
Okay. So from here you can find what is the value of theta 0 s by ds.
Yes, ma'am. It will be Ka into Kt by Rf.
Ka, no, theta 0 by ds. So this is like a closed loop system,
Yes,
no?
yes, ma'am. It will be g of s by 1 plus Ka Kt by Rf into g of s.
Ka, Kt by Rf into g of s. So will it be a plus sign or will it be a negative sign? Because here you see both the signs are plus. This is not a negative feedback. This is a positive feedback. You have to always check what is the sign in which it is going in. So if it was a negative feedback, then usually we write it as 1 plus GHHS. So for negative feedback closed loop. But in here you see that feedback is not negative. So this is a positive feedback. So you have both plus. This ds is getting added with this theta 0 into this thing. So your this sign will not be plus, this will be minus. So it will be gs by 1 minus gs into hs. Hs is something, Ka Kt by Rf. So you always have to check what is the sign of the sign in the error detector. You have a loop that you have a feedback that doesn't always necessarily mean that it will be a negative feedback, right? It can be a positive feedback also. So accordingly your transfer function will change. So from here I think you can just do the take the derivative with respect to Ka, and then you will find what is the value of. So what will be the expression for STD, sensitivity of TD with respect to Ka?
Ma'am, here we should see variation in TD or variation in KA, ma'am. It will be, ma'am, like the
KA. With respect to KA, you have to find the variation of TD. So this is TD with respect to KA.
Yes, ma'am.
So this will be, you have to take the derivative of TD with respect to KA, and then you have to, all of this as S actually. Right? So from here, you first, what you need to do is that you have to find the derivative with respect to KA, and then use multiply it with KA by TD, and then you will get an expression for the corresponding sensitivity. Is it clear?
Yes, ma'am.
Okay, so I think we can end the class here. It's already 5 past 12. So the problems that I have already shared, those are actually solved problems, but they have unsolved problems as well. So you can just try to practice a few of them, and then you will get conversant about how to proceed about when you are given with a control system, and then you have to find the sensitivity with respect to different parameters. So it can be here, instead of Ka, you might have, I might have asked you to find the sensitivity with respect to changes in Kt also. So depending on what is given, you have to correspondingly change the derivatives, and the final expression will change. Okay. So that's all from my side in today's class. We'll again continue with the second module. And in case if you have any doubts regarding the first module, you can ask in tomorrow's class. And the quiz will be from 6 o'clock, as I have already mentioned. So it will be of 1 hour quiz. So from 6 to 7, and you will have another 5 minutes to upload the scanned copy of the rough work that you have done. But make sure you do the rough work in a proper systematic way. Don't like scribble somewhere over here and somewhere over there. That rough copy also, that you are the analysis part also. So just write it in a systematic way, and then upload it in the assignment section which I'll be creating. Okay.
Ma'am, in rough work, we use a block diagram method, ma'am, for finding out the transfer functions, like, ma'am, for finding the gains, like if Ka and Kt by Rf is there. So we can write it Ka and Kt by Rf directly, like that.
Yes, you can, like, sort of, you're saying combining two blocks and representing it as one single. Yes, definitely you can do that. That is one of the correct way of doing. Not necessarily here I have represented it in two different blocks, because in the actual diagram it was given like there are two separate blocks. But two separate blocks can always be combined. If they are not loading each other, they can always be combined and represented as a single block. Like that you can do.
Yes, ma'am. How many questions will be there, ma'am, in the quiz?
How many questions? That I have not yet. I don't exactly remember how many questions are there, but 1 hour should be sufficient for solving them.
Yes, ma'am. Thank you, ma'am.
Okay. Then thank you, everyone, and all the best for tomorrow's quiz.
Thank you, ma'am.
Thank you.